a geological hazard mapping and analysis system. In this project overview, this project aims to develop an integrated system for identifying, mapping, and, and analyzing geological hazards, hazards such as landslides, earthquakes, floods, and volcanic activities. The system leverages geospatial data, remote sensing, and geographic information systems to assess hazard-prone areas and provide crucial information for disaster risk reduction and urban planning. Defining geological hazards, hazards and risk and impacts. Geological hazards refers to natural events or processes that pose a significant risk to human life, property, infrastructure, and the environment. These hazards are typically driven by natural forces within the Earth's crust on surface and can manifest in various forms. The risk associated with geological hazards is determined by the likelihood of the hazard occurring and the potential consequences it can have on communities and ecosystems. First one, earthquakes. An earthquake is the shaking of the earth's surface caused by the sudden release of energy in the earth's crust, typically along fault, fault lines or resulting in seismic waves. And risk in the earthquakes are ground shaking, surface rupture, and aftershocks. And it impacts the human casualties, infrastructure damage, and economic losses. The second one, landslides. A landslide is a movement of rock, soil, or debris down a slope due to gravity, often triggered by factors like heavy rainfall, earthquakes, volcanic activity, or human activities like deforestation or construction. And risk in the landslides are slope slope instability, rock falls, and debris flows. And the impact of the landslides are loss of life and injury, displacement, infrastructure infrastructure damage, soil erosion, and habitat loss. The one, floods. Flooding occurs when water exceeds normal levels, inundating land that is usually dry. This can result from heavy rainfall, rapid snowmelt, coastal storm surges, or the overflow of rivers and lakes. And risk in the floods are river flooding, coastal flooding, and urban flooding. And the impact of floods are loss of life and injury, displacement and homeless, damage to infrastructure and agriculture, and health risk. Fourth one, volcanic activity. The volcanic activity includes the eruption of magma from beneath the Earth's crust, leading to the formation of lava flows, ash clouds, pyro, py- pyroclastic flows, and the release of gases like sulfur dioxide. Risk lava flow risk lava flows, ash falls, pyroclastic flows, and lahars. And the impact of the volcanic activities are like loss of life and injury, environmental damage, economic losses, and air travel disruption. Enhanced risk assessment and mitigation. Risk assessment and mitigation are key components of disaster management and are essential in reducing the impact of geological hazards like earthquakes, landslides, floods, and volcanic activities. And enhanced approach to this process involves the use of advanced technologies, data analysis, and proactive strategies to predict. to predict, assess, and reduce more, more risk more efficient. And there are some geological hazards and mitigation of improving risk assessment. First one, earthquake risk assessment and mitigation. Second one, landslide risk assessment and mitigation. Earthquake risk. Sorry. Earthquake risk assessment, like enhanced risk assessment like seismic hazard mapping, probabilistic seismic hazard analysis, soil soilification assessment, and mitigation strategies are like building codes and retrofitting, early warning systems, and land use plannings. Landslide risk assessment, slopes, slope stability analysis, remote sensing, and GIS, and hydrological modeling. And mitigation strategies are slope stabilization, early warning systems, and land use and zoning restrictions. Third one, flood risk assessment, flood hazard mapping, flood frequency analysis, vulnerability assessment, and mitigation strategies like flood, flood control infrastructure, early warning systems, flood floodplain management, volcanic risk assessment, and enhanced risk assessment like volcano monitoring, eruption probability models, Lahar risk assessment. Mitigation strategies are like evacuation plans, building and infrastructure design, and Lahar barriers. Data acquisition and integration. Data acquisition and integration are critical steps in developing an effective geological hazard mapping and analysis system. The process involves gathering, processing, and combining various data sources to create accurate real-time hazards model, and map. To ensure comprehensive risk assessment and integrity and assessment and mitigation, it is necessary to collect a wide range of data types, integrate them seamlessly, and analyze them throughout advanced technologies such as geographic information systems, GIS, remote sensing, and spatial data modeling. Data acquisition and integration from the foundation of effective geological hazard mapping and analysis by acquiring a diverse range of data from geological surveys, remote sensing technologies, meteorological systems, and system data, and integrating these into a unified system. Decision makers can assess risk more accurately and take proactive steps to, to mitigate potential hazards. Leveraging this and remote sensing and real-time monitoring technologies enhance the overall capability of the system to predict, respond to, and impact the geological hazards. Analysis technique. Modeling hazard scenarios. Modeling hazard scenarios is an essential component of geological hazard analysis as it allows for the simulation and prediction of various disaster events under different conditions. By creating these models, researchers, planners, and policymakers can better understand potential hazards, their impacts, and the areas most at risk. Modeling helps in designing mitigation strategies, planning evacuations, and ensuring that communities are prepared for possible disasters like earthquake hazard scenario modeling, landslide hazard scenario modeling, flood hazard scenario model, and volcanic hazard scenario model. Modeling geology hazard scenarios is a crucial step in disaster risk assessment and management. By simulating an earthquake, shaking, landslide, moving, flood inundation, and volcanic activity, hazard models provide valuable insights into the potential impacts of these events. These models support decision makers in planning mitigation strategies, designing resilient infrastructure, issuing early warnings, and preparing for emergency response efforts. Advanced modeling tools such as GIS, hydraulic software, and volcanic simulators help create comprehensive hazard assessment that can save lives and reduce economic losses. And last conclusion, geological hazard mapping, analysis, and modeling are vital components of disaster risk asset management. Through the integration of diverse data sources and advanced technologies, we are able to predict, assess, and mitigate the impact of various geological hazards, including earthquakes, landslides, floods, and volcanic activity. Each of these hazards present unique challenges, but through enhanced data acquisition, sophisticated modeling techniques, and targeted mitigation strategies, communities can be better prepared and resilient. Ultimately, geological hazard mapping and scenario modeling uh, are, indis- are indispensable tools in fostering resilient communities. With continuous improvements in data collection technology and collaborative planning, we can better we safeguard both human lives and infrastructure from the devastating effects of natural disasters. Thank you. Thank you.